The naming system that we are going to cover for the covalent compounds and the ionic compounds are based on rules that are set forth by the IUPAC, that's the International Union of Pure and Applied Chemistry. Can't agree with your textbook on this or any other reference material, and that is learn the system. You learn the system, you will be able to communicate with any of chemists out there. It's kind of like learning a foreign language, and you learn the rules that that language has, and this one is just the rules or the language of that we're dealing with in chemistry. So you have to know and speak the language. First off, the formula unit is the smallest unit that we have been dealing with. Those are the elements that are found on the periodic table. So we've been dealing with the formula units for quite some time. For a lot of them, the majority of the elements on the periodic table, it is just the name and then or the symbol that gives us the name for that element that's on the periodic table. A couple of examples would be sodium. The formula for sodium is Na, which, as we saw from the previous unit, it comes from the Latin name with that. And yttrium, or is Y, in that why is it that way? Because that's the symbol that it is Y. The simplest are, some of them do have multiple atoms where there are two. Those ones are we'll talk about in the next slide, but they have some other ways to help them remind them, and there's a really small number of them. The ones that require two of them would be a diatomic molecule, and there are 7 diatomic molecules. If we look and just read them as we see here, it might be a little bit difficult for us to truly understand on what's actually being said with that. I have always used the idea of kind of using this kind of a play on some words, or not even make up a word for it. In a way it is. And that is you saying H, NOF, and down. And then from down you get chlorine, bromine, and iodine. So you have H, NOF, and then down. So H, NOF, and down, which, by the way, makes a 7. And if you look on the periodic table, and that's the other way of doing it, is on the periodic table, draw a 7 starting at 7. Well, element 7 on the periodic table is nitrogen. And then you have oxygen, and then you have fluorine, and chlorine, bromine, and iodine. If you draw a 7 starting at element 7, you're going to get 6 of 7. The only one that we have to remember is nitrogen. Or not nitrogen, but I'm sorry, hydrogen. Every now and then I have seen it, more recently, but every now and then you used to see hydrogen written above group 17. And therefore, if you would have drew a 7 then, you would have gotten hydrogen in that. So sometimes draw a 7 starting at 7, or H noffen down. I usually use H noffen down. Now, we're not going to use the diatomics are going to come in play when we talk about some of the bonding that they go through, but they'll really come into play on having them memorized, understanding them, looking and recognizing that they're diatomic when we get into chemical reactions. Because when we talk about oxygen, such as oxygen that we breathe, we're talking about oxygen as in O2, not elemental oxygen or just O. That's not what we breathe. I like to breathe O2. Not sure about you, but that's what it works with. The other most common element in the atmosphere is nitrogen. And when we talk about nitrogen for that, it's actually N2. So those are the two most common elements in our atmosphere, although they are actually considered to be molecules because they're not just an element by themselves. They actually are formed and are very stable when they are found with a pair of the same one of itself. So covalent molecular compounds is now you're looking at ones that are compounds. Now, I've seen these referenced as covalent compounds, as we did at the beginning of this unit slides. I've also seen them talked about as molecular compounds. And I've seen them as the long one, as we have here defined, is covalent molecular compounds. Really what you want to look at is more by definition. Compounds by two different nonmetals or metalloids, and we should be able to identify which ones those are based on our location of our periodic table that we have talked about from the previous unit. So there are some also called binary compounds, and so there's just a little bit. But the real part of it is the two different nonmetals or metalloids, and they have to be different. That's why we get the diatomic molecules from the previous one. Here I have some very common or not so common, but ones that you may or may not recognize. First one that you should recognize is H2O. That is a covalent compound. Another one that we should understand is carbon dioxide, CO2. So these are a couple examples from this list that you might recognize from your everyday life. Now, they're held together by the sharing of electrons, and this is the important part. Is a lot of people we have to understand that it's the sharing of the electrons that it comes with. It's the sharing. They do not give and take like metals do in forming of ions that we've talked about before, but it's the sharing of them. They stay neutral, and they stay neutral because they share their electrons, and therefore we do not have actual giving and taking of those electrons making ions. So they're just sharing their electrons. A molecular compound usually consists of molecular compounds tend to have low melting points. Now, low is relative based on the amount or that. Melting points, low melting point. Well, water has a low melting point, and that is 0 degrees Celsius or 32 degrees Fahrenheit. There are other ones. Carbon dioxide has a very low melting point, so much so that it's actually very specific that it almost goes straight from solid to gas. That's why it's so low. It's, if you ever took dry ice, it doesn't really melt, it just goes straight into the gaseous form. And so these are low melting points. And even a melting point of 100 degrees Celsius, which we might think is hot, is actually still low when it comes to talking about melting points, and especially those of ones that we would see at in the molecular ones, the molecular covalent compounds. And this is really when you're comparing them to ionic compounds. Now, ionic compounds, you're looking at extremely high melting points. Melting points above 500 degrees Celsius, you're definitely getting into the high range. And some ionic compounds still are not even going to flinch when it comes to potentially melting at 500 degrees Celsius. And so you're going to actually see that you would, and you could probably test this out at home, but we don't want to do that because it would create so much heat, is that you would melt sugar on your stove, whereas you will not be able to melt table salt on your stove because sugar has a low melting point because it's a covalent compound, whereas salt, table salt, has a high melting point, and that's because it's an ionic compound. So there's kind of a real big difference as where you could see one would melt on your stove and one wouldn't. I would not suggest doing that, though. Compared to ionic compounds, molecular compounds tend to have relatively so how do we name some covalent compounds? It's necessary to have prefixes. Now, it is important, and I cannot stress this enough, that these prefixes are only to be used for covalent compounds. They are not to be used for anything else. They are only to be used for covalent compounds. I would suggest writing this chart down so that you have it for reference. Although you are only going to use them for covalent compounds, you will not use them for when we talk about ionic compounds. When we talk about ionic compounds, we'll have a different way of doing that. Now, ionic compounds, when we are dealing with metal, non-metal. So these are ones that we're dealing with just the very small number of elements that are on the right-hand side of the periodic table, the metalloids and the non-metals, and they are going to be having these prefixes. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. There are more, but these are really all we're going to need for our class. To name a covalent compound, there's 2 steps. Don't try to make it any simpler than I have. I've made it as simple as I possibly can, so don't try to oversimplify it. First step is name the element that comes first. Well, that should make sense, personally, but sometimes it might not. And so you name the element that comes first, adding the appropriate prefix. This is where I might be a little bit different than some of my colleagues. And for this class, I might be okay with you using mono for the one that comes first, even though it really should not be done that way. I would really prefer that you don't, but if you do, I'm gonna at least understand what you're talking about. The second step says name the element in the formula, changing the ending to IDE, and then add the appropriate prefix, indicating the number of that element. Now, these tend to be a little bit interesting because you can drop anywhere between 2 and 4 letters off the back end of the element to name it properly. And that gets to be a little bit because how many and which ones do, because if we look at sulfur, that dropped 2 and to get sulfide. Oxygen dropped 3 to get oxide. Phosphorus drops 4 to get phosphide. And sometimes you have to read these out loud to yourself so that you can actually hear yourself. Does that make sense? Oxide, nitride, phosphide, chloride, bromides, fluoride, nitride, carbide. And those, you have to kind of say it out loud so that you're like, oh yeah, that actually does make sense. And this is the real reason why in our naming quizzes that we took, where I did not let you use fluoride as naming just the element F, because fluoride indicates that it's either an ion, or B, that it is a part of a compound. And so fluorine is not a part, it's an element, and not a part of a compound or an ion. So this is the reasoning why all of a sudden, oh, that's why it didn't let me use the IDE when I talked about fluoride. So let's practice them. Let's try some out. So we see this N2O4. Well, when I first look with this, I see N2. So I have 2 nitrogen. So I have 2 nitrogen. And so I go, and the prefix for 2 is di, and so I write di, and I don't have to capitalize it, and it's nitrogen. And then the second element I have is oxygen, but I have 4 of them. So I'm using different colors so that you can see where they're coming from. So I have 4 of them. Well, the prefix for that is tetra. And now sometimes I've seen it drawn with where it would be tetraoxide. But then I've also seen it drawn out, or written out I should say, is tetroxide, where the A on that is actually kind of dropped. And I would be okay with either. I understand that tetroxide, if you write it as with the A there, that would totally make sense to me. The next one that we look at is sulfur and 2 oxygen. Well, sulfur comes first, so we name that one first, and it doesn't have a number there, but I see that the element's there. So that indicates that there's at least one. Because it comes first, I do not put mono there, and so I just write sulfur. Oh, that my R is not looking very good on that. Oop, right here. That's good. Sulfur is what I would need to have there. Sulfur, that probably isn't even spelled right. And then we have 2 oxygen, and then we have dioxide. My I needs to be improved here just a little bit. And so we have sulfur dioxide, and so we have a little bit of there is no E on that, so it's just going to be just an R. Excuse my mistakes. So we have sulfur dioxide. We don't write monosulfur because there is just one and it comes first. So the next one we have here is phosphorus pentachloride. With that, I'm going to move our thing here. And with that, we have, how many phosphorus do I have? Well, it just writes the element's name, so it's just 1, and so it's P. And then the next part I have is penta. The penta indicates that I have 5 of them, and I have chloride. Well, you're not going to find chloride on the periodic table, but you will find chlorine, meaning that I have 5 chlorine atoms. And I put it as a subscript, just like I saw in the previous ones. The next one talks about disulfur, which means I don't have just one of them there. And so because the prefix di means that I have 2. So I have S2. Decafluoride. Deca is a prefix we haven't used quite yet, and that's 10. Deca means 10, and therefore we'll now write 10 fluorines. And the 10 is subscripted, just like that. There are a number of other examples. We'll be continuing through a lot more as we continue through notes, either in this chapter or in other chapters as well. A molecular formula shows how many atoms of each element in a molecule contains, a molecular structure, which atoms are bonded together, and how many atoms are arranged in its space. Which of the following compounds are named incorrectly? Which of the following molecular compounds names are also named incorrectly? The correct formula for tetraphosphorus trisulfide is, so back in the earlier units we talked about doing some of our electron configurations, and when we were talking about the atom. Well, this in Lewis dot structures brings back some of those similar ideas. First off, we bring back the idea of the octet rule. And the octet rule is talking about atoms will gain or lose in such a way to achieve their 8. Well, we're talking about covalent compounds, so they're going to share their electrons so that they reach their 8 electrons. For the most part, there are exceptions. One of those exceptions is that of helium gas. Helium gas will not have 8 valence electrons. The most it can have is 2, because in the 1s2 orbital, you can only have 2 electrons in that s orbital. Hydrogen also will be an exception to the octet rule, because even when it shares its electrons, the most it can have is 2 because, again, it has only the one s orbital. So how do they achieve these electrons? By donating them, becoming a cation. That means they have a positive charge. Accepting electrons, becoming an anion, the negative anion. No nukes, no nukes. Or sharing their electrons, forming that chemical bond. So that sharing that we have dealing with. Now each atom is trying to get that electron configuration to the same as that they were with a normal gas. We did a little bit of that at the end of Unit 2 when we talked about those electron configurations. Now these valence electrons are the ones in the outer shell. We talked about a little bit of valence electrons as well at that same time. Those are the ones that are in the s and p orbitals that we drew out when we did our electron configurations. So those are our valence electrons. Those are the ones that we're going to deal with when we deal with bonding. So we're not going to talk a lot about the transition metals, and they deal with the D block, and that's great and fine and whatever it may be, but we're not going to deal with them. They have some other bonding that we can do if we wanted to go on to bigger and better things. But for this class, we're going to focus on the main group elements. That's the groups 1, 2, 13 through 18 when it comes to bonding. So steps for doing this. First step when making the Lewis dot structures is to determine the number of valence electrons in the element. Then that can be found by looking at the group number. So if you look at, say, example, carbon, as we will see here, as the first example as we do this example, you will see that we have the example of carbon. Well, the number of valence electrons for carbon is determined by the group number. And carbon is in group 14. So that means that it has 4 valence electrons. So the number of valence electrons is equal to the last number in the group number. So carbon is in group 14. It has 4 valence electrons. Write the symbol for the element. That just represents the core. All the other stuff, and especially if we remember back to when we did Bohr models, all those extra rings and dots that we had to draw, they're not going to be used here. We're going to get rid of most of that and just write a C because that works. And so that's what we're going to have. And so we have writing the symbol that we have. The next one says draw 1 dot for each valence electron. By convection, this means that we draw the first dot placed on the right and then add them in a counterclockwise direction. Now there have been times where I have seen examples of this where they are drawn a little bit differently, they're grouped a little bit differently, but that's fine. This is just a way to make sure that we're at least getting a good shot at getting these correct. And they move in a counterclockwise direction. So the first dot would go on the right-hand side. Now, the second dot goes above the symbol. There, and again, in a counterclockwise direction, the third dot would go on the left, and the fourth dot goes on the bottom. And so we have that counterclockwise direction. Now, the fifth electron, if it had one, gets paired up with the first on the right to the symbol. Now, I'm going to use just a hypothetical element, and that would be Palladium. And so I'm going to have it, and we're going to look at it, say if it did have 5, and it already had it there. How does it get paired up? Well, it actually gets paired up like that, and it kind of in a way will make a little box around the compound. If you look at how it looks, you'll see these little, it'll look very kind of as if it were a box. That it has as it goes around the periodic table. You kind of just, you'll see it kind of looks like a little box around the inside. If we had that, if I made that a little bit smaller, it would make sense. But it kind of makes a little box. So you have one side there, and instead of looking at that we have. So we have, that is the part where you would have that. And we'll do some examples, and that will, I think, help clarify some of that out just a little bit more. And here we go. Here's some examples. The first example we'll look at is nitrogen. Nitrogen is in group 7. Sorry, it's not 17, but it is group 7. But no, not group 7, but element number 7. It's in group 15. So it needs to have 5 dots. So we will go 1, 2, 3, 4, 5 dots around it. Notice that I have what's called a couple bonding pairs or non-paired electrons, and then we have this other group over here that would be kind of looked at as our paired electrons, because there's 2 of them, just like a pair. The next one is oxygen, and so we have oxygen. The symbol is O. It's in group 16, so it needs to have a total of 6 dots. So we go 1. Get a bigger dot there. 1, 2, 3, 4, 5, and 6. Well, that didn't turn out so well. But you have 6. And when we look at this, we can see that there's a couple other ways in which this can bond. We can see how they start pairing up and then making that little box I was trying to talk about and show in the previous slide, which didn't quite turn out. Another example, fluorine. All right, so let's look at another example here. In fluorine, symbol is F, represents a lot of other stuff. And you might determine, hey, all of the elements within a group are going to have the same Lewis dot structure. And you would be correct, sir, or madam. And so that's what's going to happen. And you might even be able to say, well, fluorine is supposed to have 7, and I kind of get this. And so I might put a couple dots on there, and a couple dots there, and a couple dots there, and go, okay, I have 6. And there I go. And as we'll see, this is just a start. We can rotate these pairs and singles around the symbol as needed. We don't have to keep them always in this orientation. As we'll see when we start to actually bond them, that it is okay to do things such as have them in different orientations around the element. Because as long as you have it 7, it does make sense. As these are totally equivalent amounts, and it works, and it makes it so that we don't have to write upside down or try to read sideways, and some of our elements will look as if it were a different element when it's written on its side, and that's why we do that. So they can be just rotated around in a clockwise or counterclockwise directions, however it fits into the puzzle better. So how do we know which ones like to bond, how many times? Well, there are some examples of that, and we'll see that as we go through this, is that a lot of it's based on how many dots, the ones that were not paired together. Oxygen will form 2 bonds like sulfur will, and that's because it had 2 little dots that were by themselves. It's like, hey, I need a friend, and so they share the electrons so that they have a friend. And nitrogen had 3 dots all by themselves and will want to bond 3 times. Now, how many bonds they actually end up having will be determined based, again, on how many of those dots are by themselves. And so silicon has 4 dots, like carbon, and will bond 4 times. And all the halogens usually will bond 1 time, like chlorine does. And you'll see some of that when you start dealing with playing with our molecular model sets that we have and doing some of the non-laboratory based activities that I ask you to do. And it will help you understand these bonding and how many times they bond and what those bonds actually look like. So how we actually draw those bonds, it's one way of doing it is by having them pair up. And so we can see one of these dots, which one came from a hydrogen. I don't just choose this one. Maybe this dot came from that hydrogen. And we can say, oh, which hydrogen? This one. We don't know which one it is. It doesn't really matter because they're sharing their electrons. And that's what the Lewis dot structure for hydrogen looks like. As we can see, it happens more than one time, such as our example for methane. And we have 4 hydrogen around that carbon, each of them bonding to carbon or by sharing its electrons. Now, which ones come from hydrogen? Well, maybe we'll just put little dots there, and it doesn't really matter which ones are as long as one of the dots comes from carbon and one of the dots comes from hydrogen. A lot of times we'll show this by doing it that way. There are other examples as well, but we still see that everything's happening. Hydrogen's happy because it has a total of 2 electrons being shared. And if we look just at carbon, it has 8 electrons around it. That's the name of the game, trying to get this 8. So if it has 8 electrons around it, it's happy because it has a full valence shell. So we have 8 electrons around carbon, and it's happy. And hydrogen's also happy because it has 2, because that's as most as it can get. And so we have everyone's happy and everything's okay. Or at least it is in the bonding sense when we look at this. As we go through, we'll see how sometimes there are exceptions to the rules as we move forward. So let's try bonding some out. We'll do our best to kind of show where these are coming from, but we'll see how it goes, and we'll look at it. And so we have carbon tetrahydride, or better known as methane, and we'll have our carbon in the middle. And then I'm going to take, and I'm going to have 4 dots that are pertaining to my carbon. Then I'm going to take and put my hydrogen. Now I'm going to use kind of an orangish color because the molecular model sets that I have are more of a yellow, and it might not show up real well. So I'm going to use kind of a little bit more of an orangish color. Then I'm going to have hydrogen. I need to put 4 of them, and I need to put them all around here. And so I'm going to put a hydrogen and writing it out just this way there. And well, hydrogen brings an electron to the party. And those are the orange dots that you see that I brought with them as it looks. And so there's methane, and that's how we kind of work our way through it. Now, water, I'm very particular on how water is drawn. You have to be careful because if you get sloppy with this, you're going to draw water incorrectly, and it's going to mess things up later on in the unit. So we have oxygen, and I'm going to draw oxygen in red. Definitely not that color red. That should be the electrons only. So I'm going to use a pencil here. And so I got my oxygen, and then I need to have its 6 dots. And I'm going to put its dots around and go 1, 2, 3, 4, 5, 6. Well, I have 2 hydrogen to place. If I place these, I'm going to use orange again, and hydrogen's going to go 1 there and 1 there. This kind of puts them in a more correct orientation. And I got to bring a dot to the party, and so they have it there. What I don't like is when students get, I think, what I say, a little lazy and draw water out like this, because that's what they see when they Google search it. I do not like that, and I don't know very many chemistry teachers that do, and so that's not an acceptable way to draw water. Now, when there are some other rules that we do when we have these, first off, if you have multiple carbon atoms, you bond them together. So we bond our carbon atoms together, and I'm going to draw 1 carbon here, another carbon here, and I need to bond them together. 1, 2. One of them comes from one carbon, one of them comes from another. Well, this carbon has 3 around it, and this carbon has 3 around it. Well, I need to place my hydrogen now. Well, now it probably makes a lot of sense on where I put my hydrogen by placing them where those little empties are. You can see that I put my hydrogen here and here, and they each bring a hydrogen to the party. Yay, we get to share, and there we go. And now I have what is known as not dicarbon hexahydride, which can work, but better known as ethane. Ethane would be that one. And we can see that everything's there. We have 2 carbons sharing a bond together, and then also sharing bonds and electrons with the other hydrogen. Some other ones that might be a little tricky for us have some other fun aspects to it. And so we're going to have our carbon atom again. You'll get used to drawing carbon very well because it tends to be a very common one that we draw. And then we have that. Now, where I place my hydrogen and where I place my chlorine is very important. I'm going to place my hydrogen what's known as a very systematic way, and that is I'm going to place them so that my hydrogen are on one side. It might not seem as if they are on a side, but they actually are on a very specific side for that. And so we have to, we'll get into that a little bit more, but it's just trying to get you to see the proper way of doing some of this as we work through this. I'm going to use a green for chlorine because the green for chlorine it's synonymous with the halogens. We tend to use those greens for the halogens. I'm going to put that there, draw my chlorine atoms in, but I'm not done. I still actually need to put the other non-bonding electrons in. These things get really messy really fast. And you can see we're using the molecular models, and taking your time can be very beneficial. Now the next one is an exception to the rules. It has some big exceptions to it. I'm going to use a blue when it comes to dealing with the color for nitrogen, as we'll see maybe a little bit more why when you look at the molecular model sets. And so we're going to have nitrogen, and we're going to have, it's going to bond with the other nitrogen because that would make sense. And then we have there, and we have some of that happening. Well, the oxygen comes into play, and it's kind of weird what ends up happening is that our oxygen, they bring an electron to the party, but if we are careful, they're going to have something that's not very normal, and they're going to do something very weird, and it will maybe be a little confusing at first, but you might see the why, and it kind of, some things happen that those electrons don't actually kind of share there. They instead, one of them goes there, and one of them goes there, one goes there, and one goes there, because there's that other lone dot that oxygen has will also get paired up with it. Oxygen is that sibling that doesn't share well, and it always wants 8 electrons around it. Now, you might look at this and say, well, there's not 8 electrons around it. Yes and no. Because there's sharing of a couple other ones, they do have 8 electrons around it. It's just a little bit different. They are there. And so we see this is known as what's called a double bond. And a lot of times we don't draw it out this way. Instead, we draw them out usually with double lines to represent those double bonds with that. And that's what usually will happen. And it would, each bond there has 8. And so if you look just at the oxygen, it does have 8 electrons around it. And you're like, but what about nitrogen? It's got way more. Well, that's because nitrogen does something really crazy, and that's called going hypervalent. It does tend to do that every now and then. So let's get back to a more simpler one where you have CH3OH. How the formula is written actually is a little bit indicating of where this H is bonded to. It's not bonded to the carbon. It's actually bonded to the oxygen. And what does that look like? Is that we have carbon in the center, just like normal, because it tends to do that. And we have our dots around. I have 3 hydrogen in place, and so I actually will show that with that different color. And I'll place them and I'll write the hydrogen in just like I normally would. But I also now have to put in my oxygen. Well, that oxygen brings in 1. And you're like, well, the last time it brought in 2, and so why doesn't it do that? Well, that's because of this hydrogen here that we talked about that's not bonding. It's the one on the very end. It's written a little bit differently. It is actually bonded with the oxygen. And so that's why it's written that way, because it's not bonded with the carbon. It's actually bonded with the oxygen, and it's sharing it a little bit there. And there we have what's a compound called methanol. So you wouldn't be able to name this in a systematic way. You would actually have to name it methanol. And that's a little bit of what's called organic naming. And we'll talk about that, I believe, in a later chapter in this unit. So talked about some of those exceptions to the octet rule, and boron is definitely another one. It only will have 6 electrons in its valence shell. That's the most it can have. Some of the compounds with other odd numbers, boron is 1, aluminum and gallium and indium and would be other ones as well, but boron is the one that we use the most, so it will only have 6, as you can see in some of the examples here. Some other examples will be the sulfur, phosphorus. We call them. I usually like to call them the elements, the ones that are naughty a lot of times because they don't want to go hypervalent. They're taking more than they should, and so they're the ones that we tend to do that for us. And so they have that unpaired. They go. Unpaired electrons, and those are radical, which means they're not very stable. And so you have that unpaired electron that's not very stable, and therefore those molecules are not stable. Those unstable molecules mean that the compound is going to react or deteriorate very quickly in that way. So when we look at the ones that go bigger, those are hypervalent. Ones that have that oddity where do I have this extra electron here? That's not supposed to happen. Those are the ones that are called that are radical. So we have 2 big terms, hypervalent and radical, when we look at those. In covalent bonding, atoms attain the configuration of a noble gas by electron dot diagrams are superior to molecular formulas in that they which of the following molecules would contain a bond formed when atoms share 3 pairs of electrons? That would be making a triple bond. That's the end of Unit 4, Chapter 1 notes. We'll continue talking about our units as we and chapters as we continue through. Well, I guess we'll talk to you in Chapter 2.